Looks like everyone's coming in. Just let
Yeah.
me know when you want me to start talking and I will.
All right, that sounds good. Yep, I'll give everyone just another minute. It looks like we
Perfect.
still have people coming in. So,
I can see the little ticker keep going up. So yeah.
yeah, yep. All right. Well, hello everyone, and welcome to the last CPH review session. Today's topic is data analysis and informatics, presented by Dr. Anthony Disson. I know a lot of you have been waiting for this session, so I'm excited for you to be here. And Dr. Disson has taught this before, and I know that people have really enjoyed this session, so I hope you will as well. So a little bit about our presenter. Dr. Disson is a tenured assistant professor of health science in the School of Health Sciences at Stockton University. As a public and population health educator and researcher, his scholarly work focuses on intersections between queer and gender non-binary communities in the healthcare system, particularly in the areas of cultural competence, body liberation, and nutritional considerations of queer people. In addition, Dr. Disson's work explores how nutrition and health information is shared, understood, and utilized by consumers of health information, particularly through online and social media challenges. So with that, I will turn it over because I know we have a lot to cover today.
Absolutely. I know what a fun topic to leave to the end, right? Everyone's all burnt out and tired. Let's go into biostats and epidemiology. I'm sure everyone's very excited. So I'm very happy you're all here. I love teaching this subject as part of the CPH exam review. Just to give you a little background about myself, I always like to tell people I took my CPH exam 3 days before lockdown, before the world shut down in COVID in March in 2020. So in the last 5 years, it has been very fascinating to kind of witness, of course, the profoundly important role of public health. Not that everybody here on this webinar right now doesn't already know about the profoundly important role of public health, but it is just fascinating to see how much uh, awareness around the importance of this subject in this field and all of the work that we all do is. And one area that is really important within this, of course, is epidemiology, biostatistics, health informatics, and that's what we're going to be talking about today. Thank you so much for already giving me a little background about myself in terms of my work. The field of public health is one of those ones that I love being a part of because it's so diverse and it is so interdisciplinary. And so, because of that, this subject area of biostats, epidemiology, data analysis, informatics, et cetera, can sometimes be the one that causes people a lot of fear. So my objective for today is to try to alleviate that fear as much as possible. I actually think this is one of, if I may say, one of the more straightforward components of the exam, because the beautiful thing about data analysis, informatics, epidemiology, biostats, et cetera, there doesn't tend to be quite as wide a range of interpretation, right? It's either an odds ratio or it isn't, right? So by understanding these foundational areas of biostats, epidemiology, informatics, et cetera, it can not only help us better understand how we use this information to make evidence-based decisions within the field, but of course, for your interest in particular, to be very successful with taking the CPH exam, which of course you will all be successful, but in particular, you will just absolutely find this section of the exam straightforward, easy to go because it is the numbers part. And I know numbers can sometimes cause us a bit of anxiety, but there also lies the comfort of just the straightforwardness of this information. And just as a reminder, which I'm sure you've had this reinforced many times, remember the exam isn't all one area. It's, different combinations. So you're only going to get 12% of your questions in this domain, and there's a lot of information, so they can only ask so many questions. So all will be good. So let's dive on in. So the reason why this is such an important and integral part of the field and of this exam is because to make evidence-based practice part of our field and to make decisions around this, we need to know what to do with information. We need to know what to do with data. How do we properly interpret it? How do we make decisions based off it? How do we determine what is being shared with us? So one area to always remember is that we have different sources of data. So we can go with primary data sources, which are going to be the data gathered by a researcher directly. So if we all go out right now and conduct a big nationwide survey, pull that data together, that is a primary data source we have. But we also want to remember we have secondary data sources, which is when we utilize data that's already been gathered and organized and cleaned by somebody else. So for example, if you're familiar with NHANES, Nurses Health Study, BRFSS, et cetera, right? These big data sets or these big ongoing, sometimes multi-year, multi-decade studies, we can always pull information from these secondary sources as well. Data can be both quantitative or qualitative in nature. We are going to really focus today on quantitative data, so numerical data. But just as a reminder, or as a reiteration, we can also have qualitative data. Verbal, oral recordings of people's written responses or accounts of things, oral histories, interviews, etc. So we utilize all this data source to make decisions. And the way in which we make those decisions is how we best interpret that information. So all of this domain really falls under what we might call public health informatics, which is how do we use information? How do we study the world around us or populations of interest? And specifically, which we'll talk about throughout our time together this afternoon, how do we pick the appropriate kind of study design to gather and monitor and survey and obtain the information we need to make good decisions? Biostatistics is the field of statistics that uses statistical and mathematics methods to study and understand information related to living biological organisms. In our cases, typically we're going to be talking about humans, but we also have epidemiology, which is how we study and understand the distribution and determinants of health or health-related events within a population. So to be good health informaticists, we use biostats and epidemiology to understand the data that we have gathered. Typically, we are not going to be able to study an entire population unless a population of interest is so unique, is so niche, and is so small that we could theoretically look at the entire group. Typically, that's not going to happen just because the populations we might be interested in might be thousands, tens of thousands, hundreds of thousands, millions of people. So there are time-based restrictions, logistical, financial, et cetera. So in biostatistics, what we do is we try to understand as best we can what is happening with a population by studying what is referred to as a sample, ideally a representative sample. So a small subset of the larger population. We gather statistical information and we generate what are called parameters. We generate generalizations or interpretations about the population of interest. So the parameter is the characteristic gathered from the population. But again, typically we're not going to be able to look at the entire population. So we use statistics from the sample to estimate our parameters of interest. There's two major types of statistics that we'll probably use in our field within public health, descriptive and inferential. So descriptive statistics are exactly as they sound. We take the information and we're just describing what it is. We are not telling anybody what it means. We're not saying whether it's good or bad, interesting, whatever. It just is. So if you're familiar, hopefully this rings some bells. The mean or the average, right? Median, the standard deviation, making charts and graphs, etc. These are all descriptive forms of statistics. So we're just saying this was the standard deviation from the mean, or this was the bell curve, or this was the box plot that we created, the scatter plot we created. It just is. We're just saying, look, people, here is our organized information based on the study that we did. Inferential statistics is when we're starting to actually generate those parameters where we're trying to make inferences about the larger population of interest, of what it is that we're hoping to be able to understand. So this is when we use things like chi-squares and t-tests and regression analysis, et cetera, Typically here in inferential statistics, we use this to determine whether or not we should accept or reject a null hypothesis. And we'll talk more about what that means in a moment. So descriptive statistics is just here's the information as it was. Inferential statistics is this is what we think it means. This is what we think was happening in our particular study. So let's look at some common examples of descriptive statistics that you may see on your exam. In our descriptive forms of statistics, we can typically break our data or our findings down into either categorical or continuous natures. Categorical data just describes the traits, the attributes, or the qualities of our study subjects. And of course, just to make things more complicated, we can further break categorical data down into what is called ordinal, nominal, and dichotomous data. And we'll look at examples of all those in the next slide. Continuous data, on the other hand, still just descriptive, but continuous data just represents how much of something a subject or a group possesses. So this would typically be like a ratio or an interval. So a ratio of this attribute to this attribute. So categorical data, qualities, traits, just kind of those surface level things that we might be interested in. Dichotomous would be two possible values, heads or tails. So the group was exposed to the, let's say, infectious agent, COVID-19, H. pylori, et cetera, or they were not exposed. So it's one or the other, A or B. If there's more than two possible values, let's say level of education, well, that would be ordinal. And what makes this ordinal data and what differentiates ordinal data from nominal data, ordinal data has an inherent order or ranking. Kindergarten becomes before first grade. Ninth grade comes before 10th grade. Bachelor's degree comes before master's degree, right? There is an inherent step by step. We know this precedes this, which precedes this. The key thing also with ordinal data is we don't necessarily know the distance between the ranks. So for example, I have to earn my bachelor's degree before I earn my master's degree. But did I spend 10 years in between completing my bachelor's before completing my master's? Did I complete them both simultaneously in a dual degree program? I don't know. I just know that one is earned or obtained before the other. So ordinal, step by step by step, there's an inherent order to things. Nominal data is still categorical and it is still more than two values because it could be things like race or ethnicity demographics, marital status. It could be a student ID number. There's no inherent order. It's just there's a lot of different things that a person might fall into. Are they single? Are they partnered? Are they divorced? If they've been divorced, how many times have been they divorced? Are they, there's so many different options and one doesn't always inherently come before the other. Or a person's employee ID number, they're just numbers. One having an 081 versus an 082 doesn't really mean anything. Continuous deals with amounts or quantities. So intervals where is a type of data information set that we might gather where each value is equal. There's an equal distant emplacement. So like temperature, 91, 92, 93 degrees. There's a degree difference between them. So there's a very clear equal distance being present. pH levels of water that's being tested, right? We know what those spaces are numerically in between. Typically, we're going to lack a true zero in this case, in most cases. A ratio can have a true zero, and the values here, like let's say height or length or weight, the height of the values of the variables act as actual ratios. So, feet and inches. So the way that we break this information down is to really ask ourselves, are we talking about traits or are we talking about numbers? So if we're talking about general traits, categorical. If we're talking about values or amounts, continuous. Only two values, perfect, it's dichotomous. If we're looking at things that have inherent rank and order, we're talking about ordinal. Things that don't necessarily have inherent rank or ordinal, they're just nominal. If we're looking at quantities and amounts, is there a true value here? Then we're looking at ratios. If not, we're looking at an interval. how do we share this information? We don't want to just share big, gigantic, endless spreadsheets with people. So typically we want to visually display our descriptive information in a way that can be understood. When we're looking at categorical data, bar charts are typically going to be used. So on the exam, if you're looking at a question, if you're looking at an example that says, here's some information, what would be the best kind of way to visually describe it? If we're looking at categorical data, we might look at something and say, oh, a bar chart would be helpful. But what if we're looking at numerical data? Well, if we're looking at a single variable, histograms can be very helpful. If we're looking at multiple variables, typically we're going to look at scatter plots. And if we're looking at something that's based more on a time-based series, trends over time, we're going to look at a line chart. We might also, again, see questions that say, well, which would be the best kind of visualization of this data based on the purpose of the visualization? If we're making a comparison, bar charts and pie charts are going to be helpful because we get to see how things compare to one another. Again, if we're looking at trends over time, a line chart. If we're looking at how things are correlated as this goes up, this goes down, or whatever happens, that we're going to look at more of a scatter plot. And if we just want to see how things are distributed, well, that's going to be a box plot or a histogram or something like that. And then we also have, which you may or may not see, but just again, good information to know, heat maps. This is where we're going to see, a visual representation of some kind of pattern where a data set is showing the intensity of where things are grouped based on the intensity of the color used. So now that we've gone through all that wonderful information, let's do a quick check with ourselves. Which of the following would be an example of a nominal variable? Income level, state of residence, year of graduation, level of satisfaction. Pick what you think the best answer would be. If you get it correct, fantastic. If not, all is good. Just make a note to yourself of where you would shift your understanding a bit so you'd be that much more prepared in the future. So let's see where we are. All right, so I could see here we got just a little bit of the majority into state of residence, and then kind of an equal split between income level, year of graduation, and then last kind of choice mostly made was level of satisfaction. State of residence. So why? So if you got this correct, fantastic. If not, all is still good. The reason why state of residence, am I in New Jersey, Wyoming, Tennessee? There's no inherent order of ranking here. Income level has inherent order of ranking. Year of graduation, level of satisfaction, neutral comes before satisfied, which comes before very satisfied. All of the rest would have kind of a more inherent order of one follows the other with a nominal value. State of residence, no inherent order. A researcher is conducting a community assessment to determine the education level, high school education, college, grad school, etc., of community members who utilize an HIV mobile testing lab. So what kind of measurement is being used for this outcome variable? Is this a ratio? Is this nominal information? Is this ordinal, or is this an interval? Let's see where we are landing here. All right, so we get a very strong response here for ordinal, couple people for nominal interval, couple people for ratio. Very good. So ordinal, even ranks, but they're not necessarily, again, evenly spaced because we don't know how much time has passed between high school and college, etc. Very good. Ratio would be like interval. So that would be, again, more numbers. If we were looking at just kind of numerical information, quantities, it would be something like a ratio or an interval. Since we're just looking at level of education, type of education, not necessarily a quantity here. So it'd be a 50-50 between nominal and ordinal. Nominal, again, no natural order or rank. If this helps at all, the way that I would always try to remember this when I was first learning this information is nominal no. So nominal no inherent order of ranking. Ordinal is orderly. It does have an inherent order of ranking. So if my kindergarten level of thought process there is helpful to you all, please feel free to use it if that is beneficial. Just some quick reminders. You're not probably going to see a lot of heavy information on this, but you might see some charts or you might see some graphs that ask you, there's an asterisk or a star being placed somewhere. What is this referred to? So mean, the average value. The median is the middle value, which may be the same thing as the mean. Mean and median may be the same, but they may not be because certain types of extra outlier informations that are really high or really low could shift that average around, that mean around a little bit. The mode is just the most commonly given value or response given. And then range is going to be the difference between the highest and lowest value given. It may not always be based on numerical data. Again, they could be responses given about, let's say, satisfaction or, what are things you're most afraid of about XYZ health risk in your community, and people give that information. So it could be verbal or it could be quantitative or qualitative in that way, but I could still express numerically the average given information, the most commonly given value, etc. So let's look at some more areas in which we can utilize descriptive statistics. So a count is just the number of cases being studied. So we're doing a study of college students who are being diagnosed with hepatitis B or with meningitis or with flu or whatever it is that it might be. The count is just the number of those cases of phenomenon that have been found. You really want to understand proportion because we're going to see this concept come out now in a lot of the different things we're going to be looking at. So we want to understand proportions. A proportion is a count, so a number of cases of phenomenon relative to the size of the group. So the number of students with hepatitis B in comparison to or relative to all the students living in a particular dormitory or all the students in a particular university. The numerator, the top number, is going to be a subset of the denominator, the larger total number of people being studied. Typically, this is going to be given as a percentage. So a proportion could be A, number of cases, divided by A plus B, people with the case, people without the case. So A out of the total case, typically multiplied by 100. So 13% of students have hepatitis B. That would be their proportion. A ratio, on the other hand, and again, an important thing to know, are going to be students with hepatitis A compared to students with hepatitis B or vice versa. The numerator in this case is not a subset of the denominator. So the number of men enrolled in a particular course compared to the number of women enrolled in a particular course. A frequency is, I'm sorry, a rate, excuse me, is going to be the frequency that, so the count of an event occurring in a specific population during a specific period of time. So what was the rate of flu in 2022? So the count in a particular time period. So let's say we wanted to calculate this out. What is the proportion of college students with hepatitis B compared to all college students living in all of the university's dormitories? A divided by A plus B. So it would be A, the number of cases of people with Hep B, so in this case, 1,150, divided by A plus B, the total students living in all dormitories. Let's say in this case, it was 4,960 students. Simple A divided by A plus B times 100, we would say 23.2%. So very simple to calculate a proportion in this way. Just as you're not going to see a question like this on the exam, but just as a quick check-in for our own review purposes here, you don't necessarily need to worry too much about, again, seeing something like this. I just want to make sure these terms are familiar. So which of the following of these examples, A, B, C, or D, would be a count? Just give yourself a moment to think to yourself. If you said B, number of female births, correct, because it's just number of cases. Which of these examples is expressed as a proportion? So again, just take a quick second, look, see what you think would be the most correct answer here. And if you said C, well done, because it's The numerator is a subset of the denominator. So female births compared to births of both male and female babies. Very good. Which of the following is a ratio? So again, take a moment, see, share in the chat. I can't see the chat, so if you're sharing in the chat, keep it up. If you said A, well done, because in this case, the numerator is not a subset of the denominator. So male births as a ratio to female births or vice versa. And which of these would be a rate? D, because we're looking at specifically something occurring within an express time period. What type of sample do we select? So I want to understand a population. I can't look at everybody. So I want to pick appropriate samples so that my findings are actually related to the population of interest. So a simple random sample. This is going to be people within a population are just chosen at random. Everybody has an equal chance of being selected. So I have the list of all student IDs within a particular university, and I go into my computer or whatever, I have my poor grad student do this, and I say, just pick random, I need 50 people, so just, throw darts at a board and just pick 50 people, right? Or put it into a random number generator or whatever, just 50 people. Everybody has an equal chance. A systematic sample is where sample members are selected from the population according to some random starting point. So we're going to start here, but then we're going to go to fixed periodic interval from there. So every 10 people or every 3 people or every other person from here. Or we can pick what's called a stratified sample. And this is where we organize people into strata or stratum. So people within a certain age range, people of a particular gender identity, people of a particular income level, people of a particular education level. And then from each of those stratum, we're going to pick people at random. We would use a stratified sample if I need to make sure I really am getting as much of a swath of the population as possible and not, there would be something detrimental if people only of a certain income level were being selected. I really want to make sure I'm getting people from all different levels of income. Sampling distribution of a sample mean. So this can sound profoundly complicated and jargony, but let's break it down a little bit. Let's say we look at 100 people that represent a population, and we determine the average results of that data collected. So we take 100 people, average out, we find the mean. Then we look at another 100 people within that population, and then we calculate that means from another, let's say, survey or analysis. Then we do another and another and another and another. Well, we're not going to get the same mean every time, right? So let's say 1,000 people take the CPH exam this year, and if we were to take every possible sample of every 100 of those test takers, so we're going to look at this group of 100 people, and then we're going to look at this group of 100, we're going to look at this group of 100, and then we find the average CPH exam score of each of those groups of 100, we would get slightly different averages each time. So, it was the first time we took it, the average, and I'm just making this number up here, was an 86. And then we look at this one and it was a 92. And then we look at this one and it was a 77. And then we look at this one and it was a 91. And so we have all these different averages. But then if we put them all together, all these different samples from the same population, we take all the different means and put them together. This is what is called a sampling distribution of sample means. What this means is that if I keep repeating random sampling of a population over and over and over with the same sample size each time, we're going to have a lot of different means, and these will start to create what's called a sampling distribution or a probability distribution. A normal distribution is going to be what we typically think of as that bell curve. Sometimes this is called a Gaussian distribution. So we use normal distribution. We use this model we use this data to model the distribution of, again, continuous variables. We do this because we're trying to get as close to the population truth as we can. So data is symmetrically distributed about the mean. It doesn't skew left or skew right, and we get that beautiful bell curve shape where half the values are below and half the values are above the mean. This is described by the mean, the average, and then the standard deviation. These distributions are so common that most statistical tests that we'll select, so most inferential statistical tests, are designed to look at normally distributed populations. The typical rule, the empirical rule that is followed, is that if I look at one standard deviation from the mean, this will represent about 68% of all values. If I look at two standard deviations from the mean, I'll be seeing about 95% of all values. And if I look at three standard deviations from the mean, I'll get about almost everybody, 99.7. We'll look at what that visually looks like in just a moment, but a couple other probability distributions we can see. Binomial, bi meaning two. So the probability that an outcome will either succeed or fail, they are mutually exclusive. It either works or it doesn't. I design a new pharmaceutical drug to have this outcome. Did it work? Either the disease is cured or not cured. Either the effect is seen or it is not seen. So binomial distribution looks to see the probability of success from one trial to the other as being the same. Whereas the probability of each trial in of itself is independent. So again, I keep flipping that coin to see what happens. Eventually, I will see something that gives me the general probability of whether something will be effective. And then we also have what's called a Poisson distribution. And this is where we use to predict the probability of an event occurring based on what we know of what has occurred before. So this can be very useful information when it comes to public health work because we use this to forecast. So we would use a Poisson distribution, for example. Let's say if an ER in a hospital typically has 50 people admitted every Saturday night, we can use this to predict the probability of whether 75 or 100 people will be admitted to the following Saturday night. If we look at enough data from the past, and then we look at things like weather, we look at things like time of year, we can start to use that data to forecast about what we might expect, the probability of an event occurring in the future. So when we do what we were looking at, that sample mean distribution, right? So we keep looking at all those different samples. The answer is always going to be a little different mean. But if we gather them all together, and especially if we take a large enough sample size, typically at least 30 people from a population, we will get this nice, beautiful bell curve normal distribution. Even if the actual population we're studying and its values are not normally distributed, because they're probably not. Few populations are beautifully even like this. But if we follow these basic statistical guidelines and rules in our work, when we're talking about making statistical description or inference, right, trying to make predictions, if we have enough people, again, at least 30, if not more, we take enough samples, we can kind of get that predicted normal distribution. So focus on this one in particular. The distribution of ages of death within a population is typically skewed, right? Because typically in a healthy population, more people are going to die at an older age. The average age of death within a large sample taken from this population, underlying the word large here, would we expect this to have more of a right skewed distribution, more of a left skewed distribution, more of a normal distribution, or more of a binomial distribution? So take a minute here, really think about what's being asked, and again, just see what you feel the most correct answer would be. All right, let's see where we're finding ourselves. All right, so we got about half of people saying right skewed. Next most popular choice was normal. Couple people for left, couple people for binomial. What does this mean? Normal. So if you were part of the secondary majority that said normal, well done. And if you said right skewed distribution, your thinking is correct. Again, if we look at the ages of death within a population, it's typically going to be higher compared to the lower overall age of the population, because people, again, in a healthy population. But when we're looking at biostats, how would we plot this information out? If we take a large sample, this central limit theorem, just to come back here, again, even if the actual population is skewed, if we take a large enough sample, we are still going to get a normal distribution bell curve, even if the population itself is not normally distributed. The means, the distribution of means would still follow that nice, beautiful bell curve. This is why we want a large enough sample size. So if you're looking at this thing, I don't get it. What are they talking about? The key thing here is this component within biostats, central limit theorem. Even if the population is not normally distributed, if we take a large enough sample size, when we plot out our data, we will get a normal distribution bell curve. So inferential statistics, this is when we're trying to actually describe what is happening. So descriptive statistics says, here's what we found, just here's the information. But now once we get into inference, we're trying to actually make conclusions based on this information. This is where we're generalizing our findings back to the population. We want to be thoughtful and careful here, because if we misrepresent the population, because our sample either wasn't properly organized, it wasn't properly put together, or we didn't do the right statistical analysis, we will make the wrong inference about the population, and our conclusions will be, will be misleading. They'll be false. They won't be helpful. When we look at inference, we are typically can look at estimation. So we are making certain estimates about what might be happening within a population, and we'll pick estimation when a population parameter, the mean, right, the average answer to whatever it is we're interested in, is unknown. Therefore, we use the appropriate sample statistics, so the mean from our sample, to generate estimates. So what does this mean in any actual understandable English? So when we do estimates within statistical inference, we are saying that because the sample mean average was 50, again, just making this number up, we are estimating that the population mean would be about 50 as well. We're estimating here. We can't say with 1,000% certainty that they're the same, but if we've done our statistics and our study design correctly, our estimate here should be relatively correct. The other thing we can do with statistical inference is test a hypothesis. So a hypothesis is we're making an explicit statement about a particular population, what we think might happen. Key thing to understand here, because not that there's ever going to be questions that you're going to get that are purposefully confusing or misleading, but you want to be very thoughtful about how things are worded. In inferential statistics, what we do is we take our sample, we generate statistics, and then we use that data to either reject or fail to reject the null hypothesis, the estimate, the guess, right? The question about the parameter. As we look at some examples, that will hopefully make a little bit more sense. Some other couple standard things to look at here. Error. So standard error indicates how much of a sample statistic may fluctuate if we were to do the same study again and again and again. So when we're talking about error, our focus is on the sample. So if you see a question that's talking about error or standard error, it's about the sample, not the population. We're looking at the sample. When we're talking about confidence intervals, we're referring to the range of values, and somewhere within this range, there is a high probability that the true population parameter is found. So confidence intervals are focusing on the population of interest. Standard of error is looking more specifically at the study, and specifically here, the study sample. The confidence level refers to the probability that the confidence interval encompasses the true value of our population. So, oh my goodness. So when we're looking at confidence, we're talking about the population. When we're looking at error, we're talking about our study. So we're talking about our sample. This hopefully looks relatively familiar. How we express our confidence level is usually going to be 95%. There may be times we use a 90% confidence level or even something more stringent, a 99% confidence level. We're typically going to default to 95%. So what we look at here is our level of significance. So 1 minus alpha, or 1 minus level of significance, gives us our confident interval. So if I set my level of significance to 0.05, what I'm saying is if information we gather in our study falls appropriately at this interval range we've said, we are saying that we can estimate that our study truly represents the population of interest with 95% confidence. So we're really feeling pretty sure here that what we've studied represents our larger population of interest. So let's say I'm looking at this visually, and we were to be asked something like, what is the difference between, C and D here? Is there a difference? Can we say confidently that these two values are different? Just because they do pose a little bit of a difference, if we're looking at this just, graphically, the confidence interval here between C and D, they overlap. We don't have enough difference between them. So if I were to see a question comparing this type of graph and saying, is there a statistically significant difference between C and D? The answer would be no, because the confidence interval hasn't been achieved. It hasn't been surpassed. We can't say that there is enough difference between them to confidently say that that would represent a difference in our larger population. Another way we might see this is in our good old friend, central limit theorem, our bell curve, our normal distribution. So if I look at the mean, the average right here down the center, and I go one standard deviation from it in either direction, we're saying that 68% of the values are going to fall here. But remember, as we go further away, closer to 2 standard deviations from the mean, we're going to get closer to 95. So as the confidence interval increases, the interval gets wider and contains a larger range of possible values. This is why we select typically a 95% confidence interval, because we're trying to be judicious here. We don't want a lot of extra data. We don't want a lot of extra information if it doesn't really help us answer our question any better. So what will those extra possible values tell us that would really be of any benefit to the question that we are trying to answer within our study? So we want to keep that interval appropriately designed so that we get just the right amount of value, just the right amount of information to answer our question as best we can. So this is where we get into hypothesis testing and what I was saying before about null hypotheses. So a hypothesis, right? This is a statement about a population. When we are making this statement, we want to conduct a study that determines whether or not our statement is accurate. So let's say there has been a question about whether possible heavy metal contaminations in the water supply of a community are impacting the growth and development of children. I don't want to say, of course they are. Heavy metals are bad, and we have to do a massive cleanup about this, because what if they're not? What if it's not enough, or they're not the right type of heavy metal to really cause any harm? And now we're spending a lot of money, potentially generating a lot of fear on something that is not true. Nor do we want to say, well, it's expensive to clean up the water, so I'm sure it's fine, when there might really be something impacting the health and the well-being and the development of children. So we want to be able to state before we put this effort forward whether or not there really is an association between the exposure, in this case, heavy metals, and the outcome of interest, growth and development in children. So our hypothesis, we are typically going to start with what is called a null hypothesis. And the null hypothesis says there's no effect. So in this case, the null hypothesis would be there is no association between the heavy metal levels in the local drinking water and the growth and development of local children. The research hypothesis, or the alternative hypothesis, is yes, there is. There is an association. And so this is going to have to be something testable. So our research or alternative hypothesis is there is an association, there is a relationship between exposure and outcome. When we conduct our study, we are either going to reject the null hypothesis, meaning, no, the null hypothesis is false. I reject it. There is an association here. Or we are going to fail to reject the null hypothesis and say there was not enough statistically significant information to show a relationship between exposure and outcome. We want to make sure then our findings are accurate and we don't want to conduct error. So remember, error is about the sample. So if I'm worried about types of error, I'm worried about my study. We have two major types of error. We could make what's called a type 1 error. So this is rejecting a null hypothesis when the null hypothesis is true. So this would be claiming that there is an effect, there is a relationship between exposure and outcome when really there isn't. A type 2 error is when we fail to reject the null hypothesis, even though the null hypothesis is false, saying, nope, there's no effect when there really is an effect in the first place. So we want to make sure as we design our study and picked the correct, ideally correct statistical analysis, that we are not we're not committing a type 1 or a type 2 error. Because if I commit a type 1 error, I'm saying, oh my goodness, there is an effect. We got to get this water cleaned up, and a lot of time, fear, and resources might be, expended for no actual benefit to the population. And I don't want to commit a type 2 error because here I'm going to say to people, nope, we're good. And here there really is an effect, and people continue to be harmed. So, how do we know whether to reject or fail to reject the null hypothesis? And how does this have anything to do with what we were just talking about with level of significance and confidence intervals and all these other things? So you may recognize p-value. And the p-value is a number, or a p-value is a finding that provides us with a probability of obtaining a test result at least as strong as a result actually observed. So in the study, under the belief or assumption that the null hypothesis is correct. Oh my God, what does that mean? So the p-value, again, we're always focusing on the null hypothesis, is saying the null hypothesis is true. No effect. There's no difference between these things. They are not related to one another. If we conduct our study, gather our data, and now we analyze it, if we have a very small p-value, what that tells us is that the observations that we've made over the course of our study are very unlikely. It is very unlikely that what we saw would have occurred if the null hypothesis is true. So there is very strong reason to reject the null hypothesis and say there is an association between exposure and outcome. This is where p-value and level of significance come together. So the p-value is what it is. We conduct our study, we gather our data, we put it through, SPSS or whatever kind of data analysis software we're using, and it's going to start spitting out information. It's going to give us our p-values. We set that level of significance to set our appropriate confidence interval. So typically our level of significance is going to be 0.05, 1 minus 0.05, right? Where we're trying to get to that 95% significant or 95% confidence. So here we compare the p-value obtained in our study to the level of significance we've set, typically 0.05. So if our alpha is 0.05, and the p-value is 0.02, we can, with great confidence, say we are going to reject the null hypothesis because the p-value is less than the level of confidence set. If we set our alpha level really low, though, less than 0.05, we're really trying to protect that null hypothesis. We are trying to do everything in our power, basically, to protect the idea of no association. There might be reasons to set an alpha level that low, but for the most part, No, for the most part, with the kind of research and the kind of work done in our field, a 0.05 alpha level, 95% level of significance is what we're going for. If we set the alpha level of higher, let's say 90%, 0.1, well, it's going to increase the likelihood that what we're getting is a significant test result, but it's also increasing the chances that we incorrectly are rejecting a true null hypothesis. Or to come back here real quick, we're making, right, a type 1 error, and we don't want that to happen. So we are typically going to keep our alpha level at 0.05, and then we just compare the p-value. And if it's less than or equal to that, we can say there is a statistically significant relationship between exposure and outcome. In this case, if our p-value is 0.02 and the alpha level is 0.05, we can say there is a statistically significant association between kids drinking this contaminated water and their levels of growth and development. So there's a couple different reasons why we would see the values of our sample differing from the hypothesized parameter under the null. Variation, this was just a chance, or there really is a difference. There really is a difference here. So how do we know whether or not we've set up our study correctly? Well, we want to pick a statistical test that has the correct, what is called power. The power of a test refers to its ability to reject the null hypothesis when the null hypothesis is false. The power of a study is maximized by either increasing the alpha level, in which we don't typically want to do. We want to keep it at 0.05, increasing the effect size or increasing the sample size. So having a robust N, having a robust sample size means we are typically going to have better power to properly answer our question. So with inferential statistics, we set our null, no association. We set our alternative or our research hypothesis, there is an association. We select our alpha level, typically this is going to be 0.05. We select our appropriate testing statistic. So we decide what type of test we're going to do here. We set up our decision. So our p-value has to be at, this level or less for it to be considered accurate. We compute our statistics using SPSS or whatever software we're using, and then we draw our conclusions, make our summaries, and make our inferences about what we have found. So, which of these is a type 1 error? Rejecting a true null hypothesis, rejecting a true alternative hypothesis, accepting a true null hypothesis, or accepting a true alternative or alternate hypothesis. And let's see what we have found. So where are we feeling here? All right, so we get a very strong 72% of people said rejecting a true null hypothesis would be a type 1 error. A couple people said accepting the true null hypothesis. Exactly. So if you said A, perfect. If not, a key reminder. Remember, we don't accept anything, we reject. So we either reject the null hypothesis or we fail to reject a null hypothesis. So just remembering that language alone, you would have, if you knew nothing else, a 50-50 shot of knowing it's either A or B. So the ability to properly reject the null hypothesis when it's false, so our ability to reject a false null hypothesis is confidence, hypothesis testing, level of significance, or power. All right, let's see where we found ourselves here. All right, so most people, just shy of half of people said power, and then almost a relatively even split then between the others. So in this case, power. So power is the thing that is the ability of a test to determine whether it has the appropriate capacity to reject the null hypothesis when it's false. So Our ability to say this will help us reject the null if the null is not true is the power of that test. The probability of rejecting a true null hypothesis is described by the p-value, the alpha level, our confidence interval, or power. Let's see where we're thinking here. All right, so again, about majority of people said p-value, kind of an even distribution from alpha and confidence. Exactly. So if you're thinking p-value, correct. And if not, just as a reminder, p-value, probability that the difference was observed totally by chance, just random chance. So it's our ability, so the p-value, when we look at that p-value, we're comparing it to our level of significance. And if it's less than that level of significance, we're saying it is very unlikely that what we observed was random chance. There must be some kind of association here. A researcher has collected data on household income levels, as well as whether or not members of that household have been vaccinated against a particular disease. How would they properly write the null hypothesis? So if they're writing this out, in their manuscript for their study, how would they properly indicate a null hypothesis? All right, let's see where we're thinking here. All right, so we've got kind of an even split between B and D, which makes sense because those two are very similar to each other. The reason why it would be B over D, B is saying there's no difference. They're equal. A, C, and D, even D, are saying they're different. A is saying their income is greater. C is seeing the income of the vaccine is less. Even D is saying they're not the same. They're not equal to one another. So remember, null is saying there's no difference. So it would have to be they're equal. They're the same. There's no major difference between them. So how do we pick the right statistical test? Because there's a lot of these tests out here. We want to correctly select a test that will help us decide whether or not we should reject or fail to reject the null hypothesis. So there's a couple different tests, and they can sometimes seem confusing, but they're actually very straightforward. It's, again, just being familiar with their typical qualities. So chi-square test of independence. This is going to be selected when we are testing to see whether either categorical data or nominal data, not continuous data, are independent of one another. This is only used, or this will be used if we have tables that show frequency counts. So we need tables that show how much of this, how much of this, how much of this in a categorical or nominal fashion. We are going to use this if we have relatively large counts. If we have very small counts, if the value of a cell is less than 5, we would use something called Fisher's exact test. But for our purposes for the exam, just to know, chi-squared is used to see whether or not different categorical or nominal values are independent of each other. So for example, I want to know whether or not there's any kind of statistically significant relationship between a person's political party affiliation and their opinions on climate change. So here I have my table. I have my frequencies. So many people who are Democrats said agreed, disagreed, or indifferent. I would say, oh, I could see whether or not the relationship between Democrat or Republican independent political party affiliation seems to be associated with opinions on climate change. A t-test is going to be selected when the information is continuous. So just to go back really quick. So here, chi-squared, categorical or nominal, t-test, continuous. So if we have continuous data, it is randomly sampled from the population, distributed normally, et cetera, we can go with our t-test. we can use what is called a one sample or single sample t-test. And we use this to determine whether an unknown population mean is different from a particular value. Let's say we have access to the cholesterol levels of men that participated in a community health event. So we had a big community health event and we had a little table that said, hey, come do a finger prick test. Let's test what your total cholesterol is. We give them that information. Well, we've collected all this data. We have all this data collected. And I want to know whether or not there is a statistically significant difference in the mean, the average cholesterol levels of our men in this particular community event to the national level of 200 milligram per deciliter or less for cholesterol. So are our community members who came to this fair, is their level significantly different from the goal we're trying to set from a primordial prevention level? I want to know whether the protein in a particular workout drink is correct. And so I know it tells me that it's 25 grams of protein per serving, but we send it to a lab to test whether or not they're accurate or not. So one sample t-test. A two sample t-test is whether or not the unknown population mean of now two groups is different. So we're going to use this when we have data values that are independent, randomly sampled to normally distributed populations, and they have equal variance between them. So now I have two groups and I want to compare to see whether they're different from our unknown population mean. For example, I want to know how the CPH exam scores of public health professionals in DC compared to the scores of people in New York, or gender differences or treatment effects. I have drug A and drug B. Which one works better? This would be a two sample t-test. We can also have what are called paired or dependent sample t-tests. These tests are used to determine whether the difference between two sets of observation is different, which means each person in the study is measured twice. So this would be used when we have repeated measures or case control studies. So for example, I want to know whether or not a particular kind of hand washing training for restaurant employees increases the likelihood of them washing their hands before they handle food during their shift. So I will somehow determine their hand washing frequency before the training, have them go through the training, have them be tested again after the training, and then look to see if there was a statistically significant difference to see whether or not the training had any effect on people's hand washing. Or how do students do on an exam before and after a stress management program? Or how do people do when it comes to their blood pressure before and then after pet therapy? So the key thing here with dependent or paired t-testing is I have to measure the same people twice, and I need to be able to compare them both of those times. There's also this thing called a z-test. A z-test is very similar to a t-test. The difference here is that we will use the z-test if the standard deviation in the population is known and the sample size is relatively large. So typically, we're going to use a t-test, but if we have a large sample size and we know the population standard deviation from the mean, which we don't always have access to, we would use a z-test instead. We also have what's called ANOVA, or analysis of variance. This is now we have three samples. So for all these things we've looked at, we've been comparing, one or two groups. Now what happens if we have three or more samples? One-way ANOVA is where we're going to compare three or more groups with one independent variable. Two-way ANOVA is we are determining how things are affected by two independent variables. So for a one-way ANOVA, we would use this if we were doing research to test different anti-smoking interventions on tobacco usage. So let's say we have commercial A, commercial B, and commercial C. We have three different groups of people. So we have 100 people watching commercial A, 100 people watching B, 100 people watching C. And our single independent variable is Well, what happened, I'm sorry, the single independent variable is which of the, were they an A, B, or C? And then the outcome is, do they smoke or not? So I want to know which commercial was most effective. I would use one-way ANOVA. Let's say I, in addition, want to compare these interventions and know how many friends or family members does this person have who uses tobacco? Because I'm curious about how environmental exposure to other smokers influences the effectiveness of these commercials. In this case, we still have commercial, commercial, commercial as our different groups, but now we have two independent variables. Which commercial did they watch? And how many of them have peers or family members or friends that smoke? We can also use what is called regression analysis. This is used when we're going beyond just A or B, bivariate analysis. Did it work or not work? We're looking at different levels of relationship, and I want to see what's going on. Because what this allows us to do is to see correlations. How does one thing affect the other? And to what level, what strength, how much? So with regression, we can have what is called linear regression, where we are predicting the value of one variable based on the known value of another. So the dependent variable is the thing we're predicting. So I don't know, let's see, healthy eating habits of a particular person, but we do know what the independent variable is, the thing that's being used to predict, which is, let's say, income level. So we're looking to see whether income level has any influence on whether a person is eating what is considered a healthy diet. So independent, look, whatever they eat, their income is what it is. So the independent variable we know, and then we do our study, we plot things out, and we see, is there a correlation? Is there a relationship between income level and eating habits? Or BMI, and systolic blood pressure. So if we have what we see here as a positive correlation, that means that as the independent variable value goes up, the dependent variable value goes up. If we have a negative correlation, it would mean that as the independent value goes up, the dependent value goes down. And then we could say, nope, there was no correlation if we have something like we see this final scatter plot here where things are kind of just all over the place. We can also do what is called logistic regression. So this is used to estimate the probability of an event occurring based on a set of independent variables. So here, instead of having one independent and one dependent, we have multiple independent variables and a dependent variable, what we're trying to predict. So for example, I want to know who's going to have a heart attack and who will not. And so I gather a bunch of known independent variables: smoking usage, total cholesterol levels, saturated fat consumption, exercise levels, levels of stress, sodium intake. And we take all those independent variables and we put them in, and it looks to see if we can predict who is more likely to experience a heart attack versus who is not. So we're looking to compare colorectal cancer screening rates in Caucasian men and Black and African American men. We have 100 Caucasian men. We have 100 Black and African American men. They are contacted by email, and they are asked to indicate whether or not they have had a colorectal cancer screening recently. We collect all of our data. What statistical test would be most appropriate to use to analyze our data? Is this a paired t-test? Is this a chi-square? Is this a two-sample t-test? Or is this an analysis of variance in ANOVA? All right, let's see what we're thinking. Okay, so we've got larger group of people saying two-sample t-test. Kind of the next level there was the chi-square, and then our chi-square, and then kind of a relatively even distribution between the others. So chi-squared. The reason why it is not two-sample t-test and why it isn't paired t-test or anything else, this is categorical and it is non-continuous. Two sample t-test is used for continuous data. Paired t-test would be a before and an after. So it would only be a paired t-test if we looked and said, hey, have you had a colorectal cancer screening? Yes or no. Then have those same men read a pamphlet or watch a commercial or listen to a podcast or something about the importance of colorectal cancer screening, and then be tested again a year later and see whether they had a colorectal cancer screening test done. And ANOVA is only if we have 3 or more samples. So if we had Caucasian men, Black and African American, Latinx men, Asian Pacific Islander, if we're looking at multiple samples, then we would have an ANOVA. Which test would be best used for comparing the mean ages of participants between two groups? Two sample, ANOVA, chi-squared, or Fisher's exact test? All right, let's see what we're thinking here. All right, so about 3/4 of people said two sample t-test, kind of an even-ish match between the others. Exactly, because when we're looking at the means of two different groups, we are testing to see whether the unknown population of these two groups are equal or not. ANOVA would only, again, if we had 3 groups of people and comparing their ages, then we would have an ANOVA here. Chi-squared is not used for continuous. Remember, age theoretically can go on forever. And again, same thing, Fisher's exact, not used for continuous data. A researcher is measuring the body mass index between 4 different groups and is hoping to see if the means of each group is different in a significant way. What test would the researcher use here? Two sample t-test, ANOVA, chi-squared, or linear regression? Let's see where we are thinking. Very good. Very strong response here for ANOVA. Again, because we have 4 different groups that we're comparing to each other. So when we're looking at anything above 2, so 3 or more, we're going to fall to ANOVA. Can't use two sample t-tests for multiple groups. That would only be for 2. Chi-squared, same thing, can't be used for multiple groups. And if you said linear regression, understanding where you're going here, but this is only used to make predictions on a dependent variable. We don't necessarily have an independent versus dependent variable here. We're just looking to see whether groups are different from one another. Researchers are looking to estimate the probability of who will develop type 2 diabetes based on reported data linked to body mass index, cholesterol, activity, and sleep habits. Best method of analysis here. Two sample, ANOVA, logistic regression, or linear regression. Let's see where we are falling here. What are we thinking? So most people were between our 2 regressions, a couple people for ANOVA, and I understand where you're coming from with ANOVA. The thing is, with here, we're not looking at different groups. We're just looking at lots of different independent variables. So if you saw all this information and thought ANOVA, just remember, ANOVA is used for categorical predictors with logistic regression. So if you're between the 2 regressions, you were 50-50 on the right track here. Logistic regression is we're trying to estimate a single event, our dependent variable, based on a number of independent variables. So all these different things here. With linear regression, this would be more BMI and diabetes, or just sleep habits and diabetes, not all of these multiple independent variables. Epidemiology, our good friend, is really heavily rooted in this simple but very important reminder of what is sometimes called the epidemiologic triad, which is we are looking at the relationship between the agent, so whatever our exposure of interest is, this could be viral, this could be chemical, the host who is being exposed to this agent of interest. Typically here we're going to look at people, but this could be animals or this could be plants. And then of course the environment. What is the environment in which the agent and the host are meeting each other, so to speak? Couple key reminders of some key terms here. Endemic is when there is a community where there's always an elevated rate of a particular disease. So we're looking at a particular community, and in this particular region, maybe let's say something like yellow fever is always endemic, just because there's always a high level of that infectious agent in the area. Epidemic, on the other hand, is going to be an increase of a disease or a disease rate beyond what is typically expected within a community. And as we all hopefully know very well, a pandemic is when that epidemic transcends borders and we have something that's more worldwide. Here we are looking at populations again, because of course in public health, we're always looking at populations. But populations here are measured a little bit differently because in epidemiology, we're looking more at distribution and trends. So we typically are going to look at things like mortality rates, so the number of deaths that occur either in general or due to specific causes, age, etc., as well as morbidity rates, so the number of cases of a particular disease that occur within a particular population. Prevalence and incidence are very important terms within epidemiology, and they can sometimes be a little bit confusing. So just to clarify those a little bit, especially if these are terms you haven't thought of in a while. Incidence is the number of cases that are new, that develop in a population in a particular period of time. So the key thing with incidence is that they are the new cases. We can look at what is called the cumulative incidence, which is the proportion, there's our proportion again, of individuals within a defined population that will develop a new disease or experience a new event during a defined period of time. So the cumulative incidence of flu A in 2025. Incidence rate is the frequency at which an event or the development of a disease occurs over time. So how quickly are new cases occurring? So the cumulative incidence for, let's say, flu for the whole year of 2025 is what it is, the number of people in the population compared to the total population. But the incidence rate is how quickly, and is it, what is the incident rate in January versus February versus July? So we know, at what times during the year are new cases more or less likely to occur. Prevalence, on the other hand, is the proportion of a population who have a specific characteristic, disease, etc., at any given time, regardless of when it first occurred. So prevalence is not based on newness. So if I just want to know how many people in Philadelphia are living with type 2 diabetes, whether they were diagnosed today or 35 years ago, the prevalence will just tell me how many people right now have the characteristic of interest. I'm not interested in whether it's new or old. I just want to know how many people are living out, breathing with a diagnosis of type 2 diabetes in this community at this moment. Point prevalence would be the proportion of a population that has it at a specific period of time. So what are the number of current cases compared to the entire population March 15th of 2025, right? But we can also have what is called period prevalence. So what number of current cases over an interval of time. So how many people compared to the rest of the population are living with type 2 diabetes from March 1st to June 1st of 2025. So period prevalence would be more interesting for more of an infectious acute disease versus more of a chronic disease. They relate to one another. And this is an area in which people often make a lot of mistakes in how they interpret the meaning and the relationship between incidence and prevalence. Incidence of a disease, so new cases are decreasing. So let's say something like HIV. We have PrEP medications. We have post-exposure prophylactic medications. We have treatment as prevention. We have better education. We have all these things. And because of all these interventions, incidence of HIV is going down, meaning there are fewer newer cases, let's say this year. At the same time, we have incredible antiretroviral medications. We have better screenings. We have better counseling. So people who are already HIV positive are living decades and decades healthy and fine and unaffected and are living longer. So this could mean that there could be an increased prevalence. So if I compare HIV rates in 2025 to, let's say, HIV rates in 2020, there might be more people living with HIV today than there were in 2020. People can misinterpret that. Media can misinterpret that and say, oh my goodness, cases of HIV are up higher than ever. No, 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 that's not what that means. Prevalence is impacted by incidence and duration. So, yes, there may be more people living with HIV, but there could also at the same time be fewer new cases. People are just living longer with a chronic infection, with a chronic disease. Let's say the incidence, new cases, is going up, but the duration is quite short. So let's say we have a new infectious disease and people are just getting hit with it. Something like, let's say, what we've seen occur with SARS. More and more people, especially adult age people, are getting SARS. So the incidence is going up. But people aren't, I'm sorry, not SARS, RSV, excuse me. That was the example I was trying to give. More and more people of adult age are getting RSV, but the duration is short. So the prevalence could, I'm sorry, the prevalence could still be quite low. But just because the prevalence is low doesn't mean we shouldn't be concerned about the fact that why are so many people suddenly getting this disease of interest? Why, people that didn't used to get this infection of RSV are suddenly getting RSV. Now, let's say the incidence is decreasing, fewer new cases, the duration is short, not, people aren't sick with it very long, then we could see both the incidence and the prevalence go down over time. So an example that is often given for this is, imagine I have a vessel and I'm filling it with marbles or drops of water or whatever. The prevalence is the total number of drops of water or the total number of marbles within that vessel. So whether I dropped that marble in there 10 years ago or 10 seconds ago, it's in there. And that represents prevalence. Incidence is however many new marbles or new many cups of water I'm throwing into the vessel. So as incidence goes up, that prevalence is going to fill. As incidence goes down, prevalence could still stay the same, but it's not going to get filled up as much. And then either short duration, better treatment and cure, or death will cause prevalence to go down as number of people living with condition XYZ at a given time goes down over time. Another thing that we often look at when it comes to epidemiology is comparison. So remember what we were looking at before in biostats: ratios, proportions, and rates, the same exact thing. Ratio, I'm just comparing two values: ratio of male patients to female patients, death to case ratios, etc. So remember, numerator and denominator aren't subsets of each other, they're just two different values. Proportion is where I'm comparing a part to the whole. Rate is going to be that measurement of the frequency that an event is occurring in a specified period of time. So let's say a hospital administrator needs to know how many beds should be available at their current location to treat people who may walk in at any given moment with disease of interest, disease X. That hospital administrator would need to know the incidence, prevalence, cumulative incidence, or mortality of that disease. So which do you think would be the most correct answer here? Incidence, prevalence, cumulative incidence, or mortality? I don't know if we have a poll for this one or not.
We do. I'm sorry, everyone.
Oh, that's okay. I
Sorry.
just couldn't remember. That's okay. So take a moment and see, which one do you think this person, this administrator, would need to know about how many beds should be available for people that may walk in with a disease of interest? All right, let's see what we think. All right, so kind of an even split makes sense between incidence and prevalence. Pretty good 50-50 shot there, right? Just to kind of think. Prevalence. So if you said incidence and you think, come on, why not? Anybody with this disease may need treatment. So all current cases, not just newly infected people or newly diagnosed people, but anybody with this incident, I'm sorry, anybody with this disease may need treatment at a given time. So if I need to know how many beds, how many isolation units, et cetera, I might need for this disease, I need to know the total number of people with this disease of interest right now to know theoretically how many people could walk in through the doors of my hospital and need care. Just some particular measurements to be familiar with. Know the difference between crude death rate and cause-specific death rate. And then know the defining difference between neonatal mortality rates, post-neonatal mortality rates, infant mortality rates, and maternal mortality rates. Because you may see questions epidemiologically that look to say, here's a scenario. Which of these is this referring to? Because these are important epidemiologic terms. Couple different things here now with risk and odds ratios. So one thing that is very often discussed in epidemiologic work is risk, and we can have what is called relative risk, and we can have what is called attributable risk. Relative risk is the measure of the strength of the association between a exposure or a risk factor and an outcome. So with relative risk, we are looking at the incidence, new cases of a disease in the exposed, and the incidence, new cases of a disease in the non-exposed. How are they comparing to each other? That's why it's a ratio, right? They are not subsets of each other, just this compared to that. I want to know if people who are sedentary, the exposure, how many times more likely are they to develop type 2 diabetes, the outcome of interest, compared to those who are physically active? And we'll talk about different types of study designs in a second, but just as a quick preview, for this type of study, we would do a cohort study because we're starting with the exposure in mind, level of activity in this case. We also have what is called attributable risk, and this helps us to measure excess risk associated with a risk factor. So in this case, it is the proportion of disease incidence, new cases in the exposed, that can be attributed just to that exposure. So this would be a prospective study. And again, we'll look at those different types of studies in a moment. Attributable risk is important to calculate because it is the proportion of people with who have had an exposure with a disease that could theoretically have had that disease prevented if they hadn't been exposed to that risk factor in the first place. How do we calculate and determine these risks? We are going to use what is typically called a 2x2 table. And so you will very most likely see potentially questions like this on the exam, where you'll see a table like this with the numbers filled in. So a disease with the exposed, that's A. No disease, but I had the exposure, that's B. I have the disease, but I didn't have the exposure, that's C. I don't have the disease, and I was never exposed to the thing of interest, and that's D. So relative risk, we're looking at proportions here. And so it's really, again, it can seem a little like confusing at first, but it's actually quite simple. Relative risk is proportion in the exposed divided by the proportion in the unexposed, or A over A plus B divided by C divided by C plus D. But that's exactly what we looked at the beginning of what is a proportion. It's A over A plus B and C over C plus D. So in this case, it is disease compared to the total population of that subset. So it is the proportion of people who were exposed with the disease compared to just everybody who was exposed, and the proportion of people with the disease who were never exposed compared to just everybody who doesn't have who has the who was never exposed, whether they have the disease or not. So if I have a relative risk of 1, so I do my calculation, it comes to 1, no association between exposure and disease. What if I have a relative risk of something like 2? Well, there is twice the risk of disease in the exposed compared to people who weren't exposed. If I have a relative risk that has a decimal like a 1.6, that would mean people are 60% increased risk for the disease if they've had the exposure. But risk can also look at protective factors. So if I have a relative risk of 0.5, it would mean people with the exposure of interest actually have half the risk of developing the disease compared to people who never had the exposure. Let's say I took a vitamin D supplement and I'm looking at, a flu risk or something like that. And oh my goodness, people that took vitamin D had half the likelihood, half the risk of developing flu, things of that nature. So I want to do a cohort study, and I'm interested in looking at whether coffee drinking increases the risk of developing anxiety. And so I want to conduct my study at a campus. And I have 30,000 freshmen who are going to participate in this study. 10,000 of them have indicated that they are coffee drinkers. 20,000 have indicated that they are not coffee drinkers. This is a cohort study because I'm starting with my exposure in mind. I follow them during the 4 years of their undergraduate education, and of the coffee drinkers, 500 of them were diagnosed with anxiety. Of the non-coffee drinkers, 200 of them developed anxiety during those 4 year periods. And let's assume everything is perfect. No one died. No one was lost to follow-up, et cetera, et cetera. So I'm going to create a 2 by 2 table and calculate the risk. So A, B, C, D. So 500 of my 10,000 had anxiety and drank coffee. 9,500 of them drank coffee but never were diagnosed with anxiety. And then with my other exposure group, my non-coffee drinkers, 200 of them developed anxiety, 19,800 of them never developed anxiety. And now I'm going to do A over A plus B divided by C over C plus D and just do my two proportions and divide them into each other. So 500 divided by 10,000, I'm going to get 0.05. 200 divided by 20,000, I get 0.01. Divide those into each other, and I would have a relative risk of 5. Meaning, for college freshmen, those that are coffee drinkers have 5 times the risk of developing anxiety during their 4 years of college education compared to college freshmen who do not drink coffee. What about my attributable risk? So now I'm trying to see how much something could have been prevented here. Well, same thing, A, B, C, D. Excuse me. The difference here is as I calculate my proportions, rather than divide A over A plus B divided by C over C plus D, I'm going to take my proportion of A over A plus B. And from that, I'm going to subtract my proportion of C over C plus D and then multiply that by 100. So similar but different equation. So take a picture, take a screenshot, write down, just know the difference between these formulas in case you need to calculate something on the exam. So in this case, I want to know what's the attributable risk of a pollen exposure and having a runny nose. So I'm going to take my proportion, A over A plus B, so 85 divided by 102. And I'm going to subtract from it my proportion of C over C plus D, which is 25 divided by 61, which is going to be 0.83333 minus 0.4098, 4235 times 100. I would say the attributable risk of having a runny nose was 42% of that risk was attributed to my exposure to pollen. So the difference here is relative risk. I'm saying if I have this exposure, I'm so many times more likely to have this outcome. In an attributable risk, I'm saying my outcome had a certain percentage that could have probably been prevented had I not had the exposure of interest. We also can look at what's called the preventative fraction. So again, what about exposures like we looked at before that reduce the risk of disease, things that are protective or have what is called a preventative fraction. So the preventative fraction is incidence in the unexposed minus incidence in the exposed divided by incidence in the unexposed. So let's say we have a community that has never had fluoride added to their public water supply, and now they have started to begin the process of adding fluoride to their public water. And the current incidence of dental caries in children is 15%. So, as we look at incidence rates in these kids, 15% of them are going to have cavities. We compare them to a community that doesn't add fluoride to their water, and the incidence of dental caries in them is 22.6%. So, simply enough, I would take the incidence in the unexposed, so people without the fluoride, 22.6. I would subtract the incidence in the exposed people with the fluoride 15, and I would divide that by the incidence in the unexposed. Again, the people without the fluoride, and I get 0.3362. Or if that other community had added fluoride to their water, about a third of those kids' dental caries would not have occurred. They would have been prevented. We could have prevented a third of the cavities in these kids if this community had added fluoride to their public water supply. So when we think about this from its public health benefit, we would say, well, if I was trying to explain to a community why they might want to consider fluoridating their water, this kind of data can say, if we compare your community to this other community, a third less dentist visits, a third less cavities, et cetera. We also have odds ratios. The odds of an event occurring in one group versus the odds of an event occurring in another group. So how strongly is an outcome associated with the exposure? Why wouldn't I just do relative risk though? Why would I pick one versus the other? Odds ratios are going to be commonly used in what are called case controls and cross-sectional studies because we don't have incidence data to calculate that relative risk that we would for other types of studies. So odds ratio is A times D divided by B times C. So number of people who are exposed with the disease times unexposed no disease divided by exposed with the disease. I'm sorry, exposed without the disease times unexposed with disease. And so I want to know in a case control study of people with and without lung cancer, 200 of them have lung cancer, and of those 75 had previous smoked. Of the 200 people without lung cancer that we're looking at in our case control study, 31 had never smoked. So I put my 2 by 2 and I just do my simple calculation. I do AD divided by BC, and I would say the odds ratio here is 3.27. So the odds of developing lung cancer in people who smoke, 3.27 times the odds, right? So I'm looking at just to go back really quick, I'm looking at the likelihood. What are the odds if I'm a smoker of me developing lung cancer at some point in my life? About 3 1/3 times the odds as if I was not a smoker. Let's quickly go through some things about study design because I want to be respectful of our time. How do I pick the right design for my study? Well, what's my question? Who's my population? What am I interested in looking for? And also, frankly, what type of resources do I have? Am I doing a descriptive study? I'm just explaining what I see. Or am I doing an analytic study where I'm trying to actually explain what is being found? So a case study or a case report, this is just reporting people who only have the condition of interest. So this is usually typically used to educate people or alert people to a new disease. A case study of somebody coming in with antibiotic resistant form of disease. A cross-sectional study. Common example given of this, like I'm going to a mall on a Saturday and I'm just seeing who will fill out my survey. Participants are chosen just to represent the larger given population. They are not selected on the basis of their illness, and they're not based on exposure. They're just people in the mall. They're just any random snapshot of people within a population at a given time. This is being used to determine initial associations between illness and exposure, as well as to identify any prevalence of exposure. So just total number of people with exposure or illness at any given time. I don't know how long they've been having it, but I'm in the mall and I say, have you ever used social media, the exposure? Yes or no? Whether they've been using it for one day or the last 25 years, right? Yes or no, you've been using social media. Cross-sectional study. Since this gives us prevalence of either disease or exposure, we would use odds ratio because we don't have incidence, right? Again, we don't have exposure, all those different things. We just know snapshot in time. So we could say odds. Ecological studies are, again, trying to describe a larger population. And the key thing here is they can only describe the population. I can't take population level data and report on individuals because then I could be guilty of conducting what is called the ecological fallacy. This is when I make assumptions about an individual based on the findings at the population level. So I can say to somebody, smoking increases the risk of lung cancer at the population level. But I can't go to somebody who uses tobacco and say, you are guaranteed to develop lung cancer any more than I can go to a non smoker and say, you're guaranteed never to develop lung cancer. That would be incorrect. But I can say, population wise, we know people who use tobacco, odds ratio, or whatever it is that we're using, have a higher, higher rate of lung cancer. Case control studies. We will pick a case control study because people here are selected on the basis of having the disease or the outcome of interest. So I pick case control if I'm selecting people to participate in my study based on whether or not they have the disease of interest. I will pick a cohort study if I'm selecting people on the basis of exposure of interest. Typically, I will pick a case control for a rare disease and I'll pick a cohort study for a more rare exposure just because I'm curious to see whether these things have any type of, strong association with disease and or exposure. Experimental studies are often what are called randomized controlled trials. Here's where I'm trying to investigate whether an agent or an exposure causes a disease or can be used in prevention or whatever it is that it might be. So testing a new drug. And then we also have what are called systematic reviews and meta-analyses. This is where we're pooling the results of many, many, many studies together to look for commonalities and potential associations. So this can be a very helpful chart to just kind of visually identify what type of study. Am I conducting an experiment? Great. Am I randomly allocating people to group? If the answer is yes, randomized controlled trial. If not, non-randomized. But if it's not an experiment, I'm just observing people in the world. It's an observational study. Am I testing a hypothesis? No, it's just a descriptive study. This is just a moment I am describing that was observed in nature. I'm not answering any questions about it. This is just what we found. If I am testing a hypothesis and I'm determining, remember, whether to reject or fail to reject that null hypothesis, what type of sampling am I going to use? Because I don't want to make an error. So am I sampling, putting people into groups based on their exposure? So whether they've been exposed to tobacco, radiation, cigarette smokes, alcohol, etc. If I'm basing on exposure, it's a cohort study. Am I sampling people based on outcome, whether they have the disease or outcome of interest? It's a case control study. And if it's neither, I'm just going to the mall, asking people to fill out a survey. Anybody can take it. It's a cross-sectional study. I might also be out in the community collecting data and doing different types of surveillance. Active surveillance is I go out and I'm interacting actively in real time. Passive surveillance is I am relying on existing reporting system, hospital and lab reports. I'm waiting for COVID testing reports from the local urgent cares to come in. I'm not the one out there doing the testing. I'm just waiting for the reports to come in. Digital surveillance, I'm looking in the web. What's being posted on social media? What type of people are using certain hashtags on TikTok? And what are the public health ramifications of that? Or it could be a sentinel type of surveillance. This is where I'm monitoring a special community of interest and I'm looking for potential changes in how disease is being distributed within that particular community. Other common terms you might see in study design are validity and reliability. Validity refers to whether the tool, the measure, the instrument, the survey, the thing that we've selected is accurate. Does it really help represent what we're supposed to measure? Internal validity is ensuring that the relationship that we may or may not see as a result of our study is not influenced by other factors or variables. So if it's a tool with good internal validity, it's strongly made in terms of, no, what we're finding really is based on this. External validity, though, refers to can this be generalized to others? Because maybe the tool is excellent, but it's so unique and niche to this very specific group I can't really generalize it to the outside world. I can really only say this is what this specific group found. Reliability is whether the instrument is consistent. Can this can these findings be reproduced again and again and again under similar conditions? So if it's got good internal reliability, it's how consistently different items in the tool measure the same concept. So a survey or a Likert scale or something like that, is it all measuring the same things? And again, external reliability, will this be will this test help produce similar results over many administrations to different groups and people? Or is it just a one-time thing? One thing we want to be thoughtful of when it comes to study design is bias. And there's a lot of different ways we can incorporate bias. Bias away from the null would cause us to believe that there is an association when there really isn't. Bias towards the null would cause us to believe there is no association when there really is one. So how do we accidentally bring in bias? Well, there could be selection bias, where we're not allocating people to groups appropriately. We're overrepresenting certain types of subjects and underrepresenting others. We can also just have what's called observation bias, where people are included in a study, but then things start to be a bit inaccurate. So interviewer bias, maybe I'm interviewing people, and because of my body language or my tone, it's clear I'm really hoping they're going to say this versus that. And so people kind of change their answers as a result. Or about recall bias? If I'm doing a study with you and I say, oh, I'm interested whether or not if you grew up in a household with stress, how your sleep is today. So, what was stress like in your household when you were 5 years old? Well, there's all sorts of things that might have clouded or changed or influenced my ability to recall what my childhood household was like. Or we can also have what's called misclassification, where people are incorrectly classified into the wrong groups because of mistakes or other things, and that can, of course, cause distortion. We also have an interesting type of effect called confounding and effect modification. So confounders, when they enter a study, they distort the outcome because some third variable, some third thing has come in that shifts the relationship between our exposure and outcome of interest. Effect modifiers increase the relationship between an exposure and an outcome of interest. So, for example, smokers have an increased risk of lung cancer, but smokers who have been exposed to asbestos in particular have an increased risk of lung cancer. So if I am doing a study on smokers and I don't realize that a lot of my study participants work in environments where they may have been exposed to asbestos, the association that I'm finding over time of like, boy, look at this increased risk between exposure to tobacco and lung cancer might be increased beyond what would have been expected if I was working with people who were smoking that were never exposed to asbestos. So confounding or confounders and effect modifiers are both third variables. The difference is that confounding distorts an association that really is true, but effect modifiers kind of clarify the association between two because they give us more information than we would have otherwise. So we want to control for confounding factors. We don't want these things to come in and kind of gum up the works. And we want to evaluate for the potential impact of effect modifiers. So if the variable is a confounding variable, those stratum specific estimates could be used. Remember, we break people down into different stratum. If the variable is a modifier, the stratum-specific estimates for either our odds ratio or relative risk will be quite different from one another. The key thing that you would just want to know here, honestly, is just what is the difference between a confounding and a modifying variable? That's really the most important thing to know as we think about how things might be shown on the test. Another important part of public health informatics is data cleaning. So we do these research studies and we gather all this data, and it's complicated. There could be mistakes and errors and duplications, incorrect fields, improperly formatted fields. So we have to do what is called cleaning the data, where we take that raw data and we make it usable for whatever statistical analysis software we're going to use. So the characteristics of good quality, clean data are that the data is valid, it is accurate, it is complete, it is consistent, and it is uniform. Hill's 9 criteria for causality. You probably may have covered this when you were looking at chronic diseases, but Just as a reminder, that if we're trying to really say that this causes that, it has to meet these different criteria. Otherwise, we're looking at correlations. This is associated with that. This exposure is associated with this particular outcome. Within public health epidemiology, we also talk about prevention, and we can have primordial prevention, which is where we're trying to prevent risk factors at the population aggregate level. If we're looking more at individual levels, we can do that same thing. It's just called primary prevention. I'm trying to do individual education with somebody to prevent them from developing a disease. Secondary prevention or screening programs, breast cancer, testicular cancer, skin cancer, lung cancer screenings. I'm looking to see for potential early subclinical or pre-symptomatic signs of disease. And tertiary prevention is support, rehabilitation, treatment, and care. A population of women in an urban area are experiencing unusually high rates of mortality related to cervical cancer. So local public health researchers are implementing a cervical cancer screening program. Is this primary, secondary, tertiary, or primordial prevention? All right, let's see what we're thinking here. All right, so we very strongly for secondary, a couple people for primary, excellent. The reason why it is secondary, it is screening. If we were doing a class with middle schoolers or with parents of children, and we said, you can prevent cervical cancer with the HPV vaccine. Please get your children vaccinated for HPV. That would be primary prevention. We are nipping this thing in the bud before there's any risk for disease. But if I'm doing a screening for a disease, secondary prevention. Every Friday, my local health department will visit medical offices that represent various counties in a district to get a report on the number of pediatric patients diagnosed with strep throat to look for potential changes. Is this sentinel, passive, digital, or predictive surveillance? Let's see what we're thinking here. All right, so most people said sentinel, a couple people said passive, a couple people said predictive. Sentinel. The reason why it is sentinel, it's a special population, pediatric patients with strep throat. It's a niche population, and we're looking for potential changes. Last couple things, you're all doing so well. Last couple things. When we are looking at screening tests, we also look at the validity and the reliability. So validity, is it accurate? Reliability, can it be repeated? But there's a couple other things we look at with screening tests as well. The sensitivity and the specificity of that test. The sensitivity of a test is the ability of that test to correctly identify people with the disease. This is, again, just a proportion. So I know it can seem like it's just another proportion. The proportion here of A over A plus B, the people with true positives, so the people who are found to be positive that really did have the disease. Let's say this is a urine test for chlamydia. So I got my urine results back. I gave my urine test and it says positive. Well, is this accurate? Is this a false positive or a true positive? So the sensitivity of that test is the proportion of true positives divided by true positives and false negatives. The specificity of a test is its ability to correctly identify people who are negative, who do not have the disease, which is the true negatives divided by true negatives plus false positives. So I want tests that are accurate when they say yes, and they are accurate when they say no. Another couple things we can look at is what is called the positive predictive value. So I get my test, send in my urine sample, and it comes back positive for a high blood sugar or protein or chlamydia, whatever it is that we might be looking at. The positive predictive value is the probability that there really is that it's true. So it's the probability of patients that have a positive test actually have the disease. So let's say I have a test for cancer and it has a positive predictive value of 15.2%. That would mean that if I have a positive value, positive test value, there's a 15% chance that I really do have that cancer. In this case, it's true positives divided by true positives plus false negatives, false positives, excuse me. Positive predictive value is typically useful to the patient. I really want to know whether that, positive value is positive. Sensitivity is typically more sensitive, more useful to the clinician, because if it says negative, I'm not going to treat you. So I really want to make sure that that negative is true. So the negative predictive value is just the probability that the negative test is accurate. And the same thing, true negatives divided by true negatives plus false negatives. So, just to compare them to each other, and I do recommend, if you want to read what I think is a great source to discuss the difference between sensitivity, specificity, positive predictive value, and negative predictive value, because it can get a little confusing here. I highly recommend this paper. I think it's great. But in any event, just to kind of compare sensitivity, specificity, positive predictive value, negative predictive value, they're just proportions. And the only difference here is what our denominator is when we're looking at sensitivity and specificity compared to positive and negative predictive values. Sensitivity is how well a test captures all those positive cases, and the positive predictive value tells me how accurate those cases are. So, a public health researcher is studying whether an at-home HIV testing kit is accurate in truly indicating whether an individual is negative for HIV infection. That researcher is testing the what of the at-home testing kit: the sensitivity, the specificity, sensitivity, positive predictive value, or odds ratio. All right, let's see what we have here. All right, so kind of an even-ish, almost split between specificity and sensitivity. Specificity. We are looking to see the ability to identify people without. Which of these following estimates of an odds ratio would most suggest a computational error? 7.8, 1.2, negative 0.9, or 20.9? What are we thinking here? Let's find out. So most people said negative 0.9. Everybody else said 20.9, 0.9, or negative 0.9. Why? Because odds ratios are never negative. So it could be a very high number or a low number, but they're never negative. That epidemiologic triad, what is it describing the occurrence of disease as an interaction between which of these three factors? Is it person, place, and time, host, agent, environment, person, environment, and their immunity, or host, agent, and exposure? All right, let's see what we are thinking here. All right, so most people said host, agent, environment. Well done. If you aren't familiar with that, just go back, look at that triangle. It's just an important kind of foundational concept in epidemiology to know. An investigator is interested in studying people with a confirmed diagnosis of colon cancer to see if there's some association with eating a high saturated fat diet. So the control group are people without a diagnosis of colon cancer. The best study designed for this kind of investigation, is this a descriptive study, a randomized controlled trial, a case control, or a cohort study? Let's see what we're thinking here. All right, so most people said case control, couple people for cohort, couple people for randomized control. Case control. Why? It's based on outcome. Cohort would be based on exposure. So a cohort study would be selecting people who have been known to eat a high saturated fat diet versus a low saturated fat diet, and then look to see about cancer rates. But since we're looking at exposure, in this case, colon cancer, case control study. I know this is a long 2 hours. This is a lot of information in 2 hours, but again, with just some of these foundational concepts in mind, I'm going to stop sharing there. You will be fine. It will be very easy to work through. It's all just about familiarity with these concepts. Well done. Well done, everybody.
Yes, for sure. You definitely can rewatch this one. There's
Yeah.
lots of information in it. Would you have some time for a couple questions? I think we have about 5 questions in our chat, so if we could just go over those quick. So in a small sample, wouldn't it be left skewed though, since the deaths would occur most on the right, old age? I think you went through and explained this. This was the first question that you
Yes.
did.
Yeah. Great question there. So the reason why, and it can be kind of a tricky question, but the reason in that particular question it would be central is because the idea here is even if traditionally, if we were to look at a very small sample of this population, we would see an obvious skew towards, left or right, more people are going to die at older age, younger age. The idea is if we take a large enough sample size, even though the actual population does not normally distribute, we will still get that bell curve. And that's what that central limit theorem tells us is that since we're looking at a sample, if we take a large enough sample size, you will still get a normally distributed that bell curve. So it's really just to say that it's kind of this phenomenon in statistics that if you take a appropriate enough a sample size, you will see a normal distribution, even if that's not really what you would see in the actual population.
And the next question was, what is the difference between effect size and sample size?
Oh, that's a great question. So effect size is independent of sample size. So the thing with effect size versus sample size is as you increase the sample size, it makes it much more likely you will find you will see if there is a statistically significant effect, no matter how small the effect really would be in the real world. So, um, I'm trying to think of a way to describe this. So, like one way we could look at this is there's statistical significance and then clinical significance. So, if we increase the sample size enough and we do our stats, we can see that, oh, there really was an association between exposure and outcome. But it really may not matter all that much. It might be have such a small effect size. Like, let's say we're looking at the impact between weight loss or something, and then people in the particular outcome who had the exposure lost a difference of half a pound. The effect size is that half pound, which we might say, does that really matter in the grand scheme of things? Maybe it does, maybe it doesn't, but it's independent of the sample size. The effect just was what it was. But as you increase the sample size, we'll see if there is a statistically significant association there. But even if I measure everybody on Earth and have a huge sample size, if the effect is still half a pound, it'll still just be half a pound.
All right, 2 more questions,
Perfect.
and then we're
Okay.
done. Which is the best statistical test to compare the infection rate of multiple states within a sample year?
Oh, that's a good. Okay, so if we're looking to compare infection rates in multiple, so it's like infection rates of like flu with multiple year samples. That could probably typically be just a chi-square. Again, but if you're looking at multiple states, so I'm looking at Alabama and Alaska and New Jersey, then it could be ANOVA, because if I'm comparing multiple means, it would be ANOVA. But if I'm just looking at 2 states or something, kind of like I'm looking at Washington versus New Hampshire or something like chi-square or even paired t. No, it would really be it would really come to what your question is. I think would probably be a better way to me to say it. What's your hypothesis here? Because are you looking at what's influencing those um are you looking what's influencing those infection rates, vaccine programs or education programs? If you're just looking at infection rates between different states, that would really just be descriptive statistics, in which case there really wouldn't be any analysis to do. It would just be here's what it was in Wyoming and here's what it was in Tennessee, and we're just looking for changes over time.
Our last question is bias away from the null or towards the null the same as type 1 and type 2 errors?
Oh, great question. So when you're looking at whether we're being more I don't want to say when we're looking at the way that bias either towards null, kind of protecting that idea that there's no association, or away from the null, trying to see that there really is an association. A type 1 error is when we are rejecting the null. So that would be bias away from the null, which is incorrect because in a type 1 error, we're saying that we're rejecting the null hypothesis incorrectly. Whereas a type 2 error, we're protecting the null hypothesis incorrectly. So if I'm biasing my way away from the null, I'm rejecting that null hypothesis, I'd be making more of a type 1 error there.
Okay. All right. Well, thank you so much. So that is the end of our CPH review session, everyone. I've spent the last 5.5 weeks with you all. We definitely saved the most meaty topic for last. So a special thank you to Dr. Disson for being here today and powering us through all the information that we had to go over. So one last thing, when today's webinar closed, there will be a survey that pops up. If you can please fill out that survey. I use that information to help improve our review session. So if there's something that you still don't know, if there's resources you may need, let me know there because that will be something that I will work on to improve for our next review session, as well as any other resources that we have for our study resources. So with that, I'd like to say thank you for joining me on this journey the last few weeks, and I wish you luck. I know you will all do great. So thank you.
Be well, everyone.